Hi, today I want to share the paper Reinforced Learning for Control with Multiple Frequencies. It is a newly published paper in NIPS 2020, and the idea of this paper is very close to my research, so I want to have a review on this paper. The review will consist of three parts. The first part is the motivation. In traditional discrete time Markov decision process, we assume that all decision variables are simultaneously determined at every time step. Take this classic car pole for example. At each time step, we observe the situation of this car pole, and then we choose an action, and then the pole will move to another direction, and we choose another action. So in this case, we observe the environment at every time step, and we implement action at every time step. This is the traditional discrete time Markov decision process. But in this paper, the author suggests another situation, and this is the example I suggest. And for example, we put this car pole on another card, and we have two actions to determine. In addition, each action should be determined every different time step, which means that we have to move this card every 3 time step and move this card every 2 time step. So in this case, the author suggests that it will result in non-stationary nature of optimal policy, because each action will only determined at different time step, and there is some relationship between these two actions. And the author suggests propose a discrete time factor action Markov decision process to define this problem. And for this situation, the author suggests that it means that this problem consists of multiple action persistence, which means that there are multiple actions to determine, and each action will last different time horizon. So the problem is that how to optimize a periodic non-stationary policy while circumventing the exponential growth of time complexity with respect to the periodicity of action persistence, which means that each action we have to decide the action every different time step. So how to optimize this decision process, because we have to scan different time step for each action. This will lead to exponential growth of complexity. And for the methodology, the authors propose this notation. They suggest an action in vector representation, which means that they're not considering a multi-engine case, but instead they consider a single engine case, in which the engine will determine an action, a high dimensional action, and the state transition is based on the current state and the current action. And the policy over action is mapped from history, which means that the policy is determined based on the observation and decision at last time steps. And the author suggests a simple factorization is fully factorized policy, which means that each action in the high dimensional action vector has no relationship to each other. I think this assumption. I think if we remove this if we I think if we remove this assumption, then this problem can be regarded as a more flexible multi-engine case, which can be a research direction, I think. And this policy, for this policy is very intuitive because we have to choose the action, we have to determine the high dimensional action, and each element in this action vector should be decided every different time step. For example, for this action, it should be decided every cm time steps. So each action will be decided in different time steps. This is the major difference between the traditional Markov decision process. Actually, to formulate this problem, we just need to impose each action to be kept persistent by introducing constraint on fixed time steps, which means that if you don't want to if there's not a time to determine the certain action, you just keep it the same as the last time step. So by simply add this constraint to the policy space, we can have we can define this discrete time factor action Markov decision process problem. And through this definition, the action ATM is decided every cm time step, but it will implement this action at every time step, which means that this problem is actually suggested we have to implement action at every time step, but the decision of each action is determined at every different time step. And the goal is to find the optimal C persistent policy, which optimizes expected cumulative rewards. This is similar to the traditional reinforcement learning problem, but in this case, this policy is called C persistent policy because each action in this policy will be kept the same in different time steps. And this is a simple example to indicate the FAMDP problem. For example, there's two actions to determine, and each action will determine in different time step. For A1, it is determined every 2 steps. So the first 2 steps, the action is the same, and then the third step, the action is needed to be determined, and they choose the action to be 1, and this action will be the same at the following next time step. For A2, it is needed to be determined every 3 time step. So in the first three time step, the action will be the same, and next 3 time step, the action will be the same in the same way. So in this problem, we cannot ignore the action persistence to find optimal policy. Why? Because if you want to get in this decision process, if you are in a state x0 at the first time step, you have to move to x3 to get the largest reward. But if you regard the action, but if you ignore the action persistence, you just choose A11 to move to next step, then because it will keep the same in the next time step, so it will move back to the x0. So you will never go to the x3 based on without considering the action persistence in this Markov decision process. So the author suggests that we have to have we have to specifically consider the action persistence. However, if we follow action persistence scheme, then we have to explore policy in action space with time complexity of a to the power of L. L is the time steps. Why? Because at each time step you have to export or what's the steps of other actions to determine the current state value of current action. So it will lead to a exponential growth of time complexity to estimate the optimal value. So if we consider time step for each action, there will be an exponential time complexity. And the author suggests a policy evaluation and improvement for C persistent policy. The first is that they give this notation to indicate that the action projection, which means that the agent choose decision every time step, but then use this function to retain the actual change action with respect to the C persistence scheme. So this is just a mapping function to regulate the action at current time step. So it means that we choose action, we implement action at each time step, but the action exchange only based on the C persistence scheme. And the author suggests a one-step Bellman operator, which they use to map value function to value function based on next step value function with respect to current C persistent policy. And if they compose the multiple one-step Bellman, compose L one-step Bellman operator, it will lead to a Bellman operator for C persistent policy. In this case, that the Bellman operator is established to estimate the state action values for each time step for each state action pair. Then the author suggests this theorem, which means that the L-step Bellman operator is gamma to the L to the power of L contraction. I haven't seen the proof of this theorem, but if this theorem works, it means that the L-step Bellman operator with L-step Bellman operator, the error of estimating value state function for each state action pair is limited. This is the contraction theory. In this case, it means that we can estimate the state action value accurately enough to perform policy evaluation. And if you can see the one-step Bellman operator in this situation, we can see that the time complexity to apply this formula is O x state space to the power of 2 and multiply with the action space, which is the same as the traditional reinforcement learning problem, traditional policy evaluation problem. Next is, after the evaluation of the policy, we need to do the policy improvement to update the current policy. And the author also suggests another theorem, but I have not seen the proof because I have not found an appendix. And it's very similar to the traditional policy improvement. They suggest update policy based on greedy policy. And by introduce the policy evaluation and improvement algorithm into an actor-critic network, we will have an action persistent actor-critic. And the largest difference between the action persistent actor-critic and traditional actor-critic is that they considered L time step at each update, at each train procedure. Because the C persistent policy means that we have to the C persistent policy has the feature of periodicity, and this algorithm is to use to train the actor-critic network. For example, in traditional actor-critic problem, we just have to consider disks and disks, but in this problem we have to consider n L time steps. We have to consider L time steps. So this is the major difference. And for the experiments, the author suggests two different experiments. The first is the multiple continuous control task, where each joy has a different degree of persistence of each action, which means that this joy has the action of this joy is determined every time step, and the action of this joy is determined every 2 time step. And the second case is the traffic control case. There are 4 intersections, and each intersection will maintain a traffic signal signal scheme which consists of some phase to determine, and the cycle of, and according to the author, each intersection will have different action persistence, which means that for this intersection it will determine the action every 2 time step, but for this intersection it will determine the action for 3 time step. The action is to determine the phase of this traffic intersection. And actually there are 4 intersections to determine, so the dimension of the action vector is 4. And the author suggests 4 baselines to validate the performance of their method. They suggest that there are no available methods that consider the FAMDP problem, so they use traditional reinforcement learning problem as state-of-the-art baseline SAC, and do some by imposing some constraint to fix the problem, to validate the performance of the proposed method. The first baseline is a traditional SAC, and it is trained in no action persistence environment. The second is the SAC that is trained in action persistence environment. The third is called SACL, which means that it is trained in action persistent environment, but the observation is different. The observation consists of current time step, which is presented by one hot encoded vector, and the last L actions. And there are also a baseline called SACL compat, which is very similar to the SACL, but at this time they only use the last action. But and this baseline is used to indicate that what's the performance if we totally not consider the action persistence. This is used to indicate that if what the state-of-the-art baseline used in consider the action persistent environment without any other structure. This is called the SACL is used to indicate that if we consider the action persistent environment and have certain information to highlight the action persistence, but without any further structure, what's the performance. Second, the fourth is used to have more compact information, because they only use last action, which means that the information is not as redundant as the SACL. And this is the performance of the methods. The result indicates that the proposed method is the best in all the five scenarios. Okay, that's the literature of the that is the literature review of the paper, and there is many proof I have to go through it because the paper is published recently, and the appendix is not online, so I have to wait for their appendix to see the proof. And by the way, it's a very interesting paper, and the notion is creative, and is really close to my research. Thank you.